My name is Catherine Gamboa, and I am the Machine Learning Global Educationalist at Blue River Technology, which was purchased by John Deere about, I think it was 3 years ago. And our role for John Deere is to create precision agricultural machine learning projects for John Deere vehicles. And so I've taken lots of classes on machine learning, and I've taught lots of classes on machine learning. And in all those hours of learning and teaching, one topic has never come up. So I would like everyone to type in the chat which of these 4 topics you think has never come up in any class I've taught or taken. Chihuahuas and blueberry muffins look alike to some ML models. Machine learning models use hardware to perform rapid, low precision floating point math. A robot judge of beauty competitions was biased towards one race. Or machine learning infrastructure is complex. So I can't see what people are typing in, so someone will have to tell me if there's a particular number that people are picking.
4, number 4 so far.
Number 4, darn it. Yes, so let's look and see. It's not muffins or Chihuahua, because I actually discussed this topic in a class I've taught, where Chihuahuas and blueberry muffins look alike. It's not this topic, where I've taken a class. I used to work at Google before I worked at Blue River, and I took a class on GPUs and TPUs at Google. And it's not this topic, where I teach a class of biased data leads to biased models. It is indeed machine learning infrastructure is complex. In all the classes I've taken and taught, I've never once heard this conversation or topic come up. And it's interesting because machine learning models don't live in space. And machine learning classes, everyone talks about the inputs and the outputs of the model, but no one really discusses how the inputs get to the model and what happens to the outputs. Usually, there is some hand waving and the user of the model lives happily ever after. So what I'm going to cover in this class or this presentation is what is the process of developing an ML model? And we'll start by looking at what actually happens behind the hand waving and the happily ever after. So, machine learning project begins when someone becomes frustrated, thinking there must be a better, faster way to do a particular task. And the idea of using machine learning is born. So, we're going to step through a project. We're going to create a product similar to AutoStitch. We're going to collect a bunch of images from the user and stitch them into a panoramic photo. And the first step for a machine learning practitioner is to gather images. Lots of images, I mean millions. Just collecting the data for a project like this is time-consuming and expensive. And to prepare images for machine learning can cost anywhere from 80 cents to several dollars for each label. And remember, we need millions of images. So the images for training the model need to be before and after photos. So for example, these 2 photos are going to be stitched together, and the final stitched image is this one. So we'll need images that have been stitched together from anywhere from 2 photos up to, say, 10. We'll say 10 is the limit of our product. And notice the image has a black strip along the right side. This is the residual from the algorithm that we're using to stitch the photos together. So that will have to be cleaned up before we serve this to the user. Now, the model needs to be trained with those millions of images, but there's a slight problem. The machine learning practitioner isn't going to train all the images on the model all at once. In fact, the practitioner may want to start with a small subset of the images or even test different subsets for bias. So, how does the practitioner determine which images to select? Metadata. Each image will need metadata and search software to find the right images amongst the millions of images available, which means to train our model, we're going to need the help of software. At Blue River, we have an entire team of software developers that work on keeping our 4 million images searchable. For example, an ML practitioner could ask for images of corn at dusk in Iowa with high weed pressure, meaning with a lot of weeds in the fields. And the search engine will find all the qualifying images and return them in less than a minute, which is actually it may not sound impressive when you compare that to what Google can do, but it is impressive. And once there is some data, the practitioner creates the model. And so here's another question for all of you. A number of studies have been conducted to determine the amount of time spent creating the model in a machine learning project. Take a guess at what you think the amount of time is spent creating an ML model.
We have a lot of trees.
Okay.
2, 10, which is not.
Oh, they must mean 10%, which is the 3.
Oh, yeah. 7, 5, 4, 6, all the options.
Oh, wow. Mm-hmm.
Thank you, everyone.
Okay. Correct answer is, you'll be surprised, 2%. About 2% of the time on a machine learning project is spent creating the model. It actually takes almost no time to create the model, especially nowadays. So the model's ready. And so now what we need to do is productionalize it. Productionalize it. When the model is ready, it's finally trained and is performing at an acceptable level, it's time to release it into the wild for our users. So the first question we need to ask ourselves, how do we get the images from the user's camera to the machine learning model? The image needs to be prepared for the model, which may mean changing the image to grayscale or modifying its size or doing different tasks to it. We need to make whatever our users are giving us, we need to make those photos of the same format that the model has been trained on. So if the model has been trained on some odd photo sizes, we have to either go back and retrain the model or else import users' photos and retrain them or reformat them to odd sizes or formats. And so who builds this pipeline? Yes, software teams. And once the model has made a prediction, in our case, a stitched photo is the prediction, we need to do something with it. And the first thing we need to do is clean it. So this is where we have a prediction and we do what's called making a decision. Sometimes the decision is simple as cleaning the photo before we give it to the user, or it might be something more like if the model does something like predict, I don't know, miles per gallon of cars, we might want to say, give them a range of cars they can purchase, I don't know, in that miles per gallon range. And so again, software developers. And now the photo needs to be served to the user, which will require an application of some sort. So software developers need to create an application, but this is not all that happens in a machine learning model or machine learning system. There is much more going on behind the scenes. Each of the images that is being stitched together must be saved. And each stitched photo that our model put out, which is the prediction, must also be saved. And then the decision about the prediction needs to be saved. And finally, we need to know if our model was right. So did we stitch the images together correctly? We can do this in a couple ways. One is we ask the user if they like the stitched image. And the other, we monitor what they do with the image. For example, do they save it on the phone? Do they email it to others? And all of that saving and storing is, again, done by software. And of course, getting it wrong can lead to funny images that people might want to keep on their phone. So we have these 3 images that we are asking the model to stitch into a panoramic. And this is the panoramic it stitched it into. So obviously something was not quite right since it made that skier a mountain. So models aren't just deployed and forgotten. They need to always be updated. There are 2 copies of the model. One is the production model. That's the one our users are using. And the other is the playground production model. And this is the one that we are continuously training. All new images from the users, the stitched photos, and the correctness of the photo are used to train and improve the playground model. So here's another question. If a machine learning model is never updated, how long will it be before the model is out of date?
We have 5. Everyone says
Pretty
5
much.
until now.
Yes, 5. And that's actually a standard machine learning answer. It depends. If we were doing a spam filter, an hour might be enough for our model to be out of date. Consumer fraud models might be out of date after a day. Search engines could be out of date after a week, especially if you're searching for restaurants or bars during a business downturn. And 1 month, it could be out of date if, say, you're using it in a very controlled environment like a production floor and conditions change. So the playground model, the production model are always monitored. And when the playground model performs better than the production model, they're swapped. Or actually not swapped, we remove the production model and we put in the playground production model. And since we don't want to do this manually, because we could be doing this depending, either every hour, every month, every day, we want it done automatically, which again requires software. And finally, the new playground model and all the data used to train it must be versioned and stored. And so when we look at this and we just say, let's color in all the places where we would need a software team, we can see that when we look at the complete machine learning system, a large portion of the work is not machine learning. Granted, some of the areas I've marked might be considered operations, but not always. It depends upon where your machine learning system resides. Okay, so anyone have any questions about this step before we go on to the next? Okay.
No questions so far?
No questions? Okay. Machine learning infrastructure is complicated. So creating algorithms is still complicated. In fact, it's a PhD level complicated. And using machine learning can be incredibly easy, like the difference between implementing quicksort and calling the qsort function. The majority of projects implemented today use open source models that have been tested and debugged. Advances in machine learning is growing at an incredible rate, and time is on your side. If something can't be done today, wait a little while and you might be able to do it in the near future. For example, in 2004, the first real attempts were made to make photo stitching algorithms. The algorithm was slow and not very accurate. And the tutorial just to use it was 70 pages. And today, I can teach you to use the photo stitching algorithm in 2 hours, and you'll get results like this. And to understand why machine learning infrastructure has gotten so complicated, let's take a quick look at the history of machine learning. This chart shows machine learning gaining in popularity twice in the past, and in both cases, failed to meet expectations and so fell out of favor. These periods were known as AI winters, and these are times when little progress was made in the field of machine learning. And as you can see, machine learning has been enjoying a resurgence in the last couple decades. But here's what I want you to look at. Look at the red line I've added to the chart. It's at approximately the year 2002, which is when machine learning really started to take off. So I want you to tell me, why did machine learning have a resurgence in 2002? And this research, and here's a hint, the surge in popularity is also the reason for the increased complexity.
Four, five. Five,
4 and
4. 5, 4.
Yep, people are pretty much picking those two. Yeah, I'd probably pick one of those two too. The correct answer, 4. Amazon. Amazon had a lot of servers that they only used during peak buying periods. Because if you recall, Amazon started out as a book seller and then went into selling all kinds of retail. And so they kept buying servers, but they only used them during peak buying periods, like around Christmas holidays or gift giving occasions. And so what they said was, let's rent out our excess servers. And let's see how this changed the history of machine learning and complicated the infrastructure. So in 2002, Amazon had a lot of servers. They were not being used except during peak buying times. So Amazon created AWS, Amazon Web Services, a company that rented out server and compute time on the Amazon infrastructure. This meant that many of the constraints to machine learning were removed. Once AWS created the first public cloud, people had unlimited compute power, unlimited memory, and scalable infrastructure. They were no longer confined to small models and small data sets. They could think of bigger and better models and find harder and more complex problems to solve. And with the increase in compute power comes increasing complexity. There is no way around it. Machine learning infrastructure is complicated. Every layer of the stack we're seeing here is, we're beginning to see new platforms and tools emerging that are optimized for machine learning. To take full advantage of machine learning models, we need to be able to scale up or down immediately as needed, and we need to do this quickly, and we want to abstract the details away from the user. All reasons why the infrastructure has gotten more complex. But in that same period of time, using machine learning has gotten easier, where software development has not. Okay, so I'm going to go on to the last topic. Does anyone have any questions? Okay, what I'm going to be talking about in this section is about mismatches in the infrastructure. This is because, as you saw, the complexity of the machine learning infrastructure, there's a lot of opportunities for mismatch. And so let's stop and take a look as to why it happens and what we can do about it. So there are three perspectives when it comes to most machine learning projects on the cloud, but there are also machine learning projects where they only go to the cloud for data storage. Everything else is done on the edge. For example, on your phone, we actually have a project at Blue River where we call it the See and Spray. We've built this for John Deere. And it takes photographs of fields as the sprayer is driving through them and sprays every time it detects a weed. So we actually do all of the machine learning and storage on the vehicle itself, the sprayer, and then upload it at the end of the day or end of the season. But there are also, so this is what is also known as machine learning on the edge. So machine learning engineers or data scientists concentrate on the model, and software engineers concentrate on creating the system. And operations, if you're in the cloud, concentrate on the flow of data through the system. And since both software and operations tasks are often done by the same group of people, if you're not in the cloud, and depending on the project, I will group them together in this presentation. So one of the more interesting metrics for machine learning projects involves model inference time, which is actually extremely important if you are working as a software developer on a machine learning project. Again, here's our software block diagram, or I guess our machine learning system block diagram. And when we talk about model inference, we're actually talking about the time from when the picture is selected by the user, or the pictures, to when it's actually presented to the user as a stitched photo. That's the amount of time we're looking at. So it could be a while, or it could be very fast. Is 5 seconds the right amount of time? Maybe less. If you've ever waited for an app to finish, 5 seconds can feel like an eternity. And machine learning models are fast and usually cannot get any faster. So any time savings that comes in the infrastructure or in the system has to come from all the infrastructure. I'll tell you, at Blue River, we have a task we have to complete. We have to take pictures, run it through the model, predict weed or plant, then spray, take a picture of what we sprayed, store all that. Has to be done in less than 70 milliseconds. And so I will tell you, our software engineers spent many, many days getting that time from the camera to first taking a photo to actually spraying, getting that down below the time. And not only is it critical in, say, photos, it's even more critical. For example, this is a simplified block diagram of a self-driving car. How much time do you think between sensing an obstacle and deciding what to do about it? And so I'm going to simplify our system, our block diagram, a little bit. And this will highlight some areas of concern. These are areas that are called mismatches. They are transition points from machine learning engineers to data scientists to software developers or operational people. And mismatches will greatly affect the performance of your system. It could even keep it from working. So this can happen. Compute resource mismatch. This can happen when the model is tested on a faster or larger computational computer. And when this happens, the model will either not work or not work correctly. And this is a very common thing. Usually machine learning engineers, at least I know at Blue River, are given very expensive, very high powered. I think each one is in the $20,000 to $30,000 range computer, and they run their models very fast. And then they say, we're getting all these great results. But then when we load it onto the little edge computers that we use, things don't go as well. A model, here's another one, data distribution mismatch. The model was trained and tested on data that is different from the operational data. This is something that is drilled into machine learning engineers over and over, but they often doesn't sink in. What happens is they make an assumption that the pictures they took, say, with the cell phone, they used, say, an older cell phone. It's nothing like the newest cell phones that everyone is using. Or maybe they used ones that they didn't take flashes, or the users are using flashes. And what happens is the data that the model was trained on is nothing at all like the data that's coming from the user. And what happens is the model no longer works correctly. And you'll start to get very strange stitching. Instead of stitching like this, it'll be like this or like this. You'll get pretty much a mess. And the next one, API mismatches. This is when you have to use large amounts of glue code to fix data discrepancies. So this is when we have, it should be a very smooth process. What comes out of the model should be exactly what we were told was coming out of the model. And unfortunately, it's not. And so to make it work, we end up using a lot of glue code, which actually in the long run starts to cause trouble, because now you have a model or a machine learning system that's very finicky. And finally, testing data mismatch. This occurs when the software developers cannot replicate the test conditions. So what happened was the machine learning engineers trained their model, and then they tested it, and it worked great. And they gave it to the software developers and said, stick it in, it's good to go. But the software developers could not replicate that test condition, and so could never fully test the model. And so now you get into, is the model working or not? Which is a kind of important question to answer. And then finally, tools are not set up to detect diminishing model accuracy. This comes about when people put in machine learning systems and they don't really stop and think about what will happen if the model gets worse. Everyone thinks about the model getting better. Oh, look, they'll say, they have plans, right? We had plans when our playground model got better. We were going to swap it with the production model, but we really don't have plans for what happens when the production model gets worse or the playground model gets worse. And so what happens is the model slowly gets worse and worse and worse. And this happens lots of times with things like cell phones. This would be a typical thing that might happen with our product. All the software was designed for 2013 cell phone cameras, and now we're in 2020. Cell phone cameras are so much better now, and they do so many other things. Suddenly, our model can't handle it. Either it's maybe too many pixels, or it's picking up too much. There's too much information on each image. And for whatever reason, our model is slowly degrading. but it's not being detected. And this is the kind of thing where it wouldn't be detected until, unfortunately, it got so bad that people started complaining. And so each of these mismatches can sink an ML project. So most of these mismatches could have been avoided if the machine learning practitioner had communicated a little more clearly. And so now we come to the point of the presentation. What is the role of the software developer in machine learning projects? Basically, yeah, someone who has to make the project a success. So right now, everybody is quite enamored with machine learning, and many companies and many projects fail because they forget the point of the project, which is not to have a beautiful machine learning model. It's to solve a business problem. So someone has to keep their eye on the prize, and that someone is you. So all the responsibility comes right back on you. So the software developer is going to have to figure out how to solve the mismatches, or better yet, don't let them happen. And the best way to reduce mismatches is to communicate often and with detail. Don't become complacent that the data into the model, the output of the model, and the model training environment will stay the same. And don't assume that what the ML practitioner is telling you is necessarily correct. They may have forgotten that they made some changes recently or in the far past and just neglected to document it. And so basically, so if you remember, I showed you the slide as at the beginning of the presentation. It's best to always assume the project is drowning.